There we go. Alrighty. So today's in-class assignment, as per usual, has to do with the what should we call it? The video lecture on superposition. Sorry, I was having mental problems there. So does anybody have any questions about this in-class assignment or any of the homework problems or anything like that before we jump into today's lab? Hopefully this is pretty straightforward, but maybe not. Pardon? Sure. So when using superposition, we need to analyze the circuit with, it doesn't necessarily have to be one independent source on at a time, but for this one, there's only two independent sources in there, so that's how it's going to be. So we'll analyze the circuit to solve for Vx with the current source on, voltage source off, and then with the voltage source on, current source off, and add the results of our analysis together, and that will give us the correct answer as if we had analyzed it with both sources on at the same time. So let's redraw the circuit. Let's start with current source on and voltage source off. So with our current source on, we are going to have our resistor in parallel with our current source, which is direction up. A resistor, a resistor, a resistor. And what do we do to turn off our voltage source? Short circuit, that's absolutely right. So let's see. Here is Vx, 17, 1, 10, 7, I think that goes to 20. Alrighty, so how can we go about analyzing the circuit in the most efficient way? Anybody have any suggestions? Let's talk about that. So there is a 10 ohm resistor and a 7 ohm resistor that are connected in parallel, but they're also in parallel with a short circuit. What does that mean? What's the resistance of a short circuit? 0. So you'd have, no, go away. Oops, God, what just happened? That's the wrong thing. There we go. 1 over 10 plus 1 over 7 plus 1 over 0 to the negative 1. So this is a small number plus a small number plus infinity. So it looks like infinity to the negative 1 power, which is 0. So whenever you have resistances in parallel with a short circuit, those effectively what it means is the current is going to flow through the short circuit. None of it's ever going to branch off and flow through the resistors. So these guys, since we know no current's ever going to flow through them, we can treat them as if they were open circuits or really not even there. Or we could just replace all of those resistors with a short circuit, whatever you feel like. So that means that our circuit has simplified to a current source in parallel with two resistors. So how are we going to solve for that voltage Vx prime? So if we do current division and then Ohm's law, so this is an opportunity for me to show you guys something, okay? So let's do current division. So the current, let's call it Ix prime, is going to be 1 amp multiplied by 1 over 20 ohms plus 1 over 17 ohms plus 1 over 20 ohms, like so, using current division, right? So let's figure out what that is. 1 times 1 over 20, 1 over 20 plus 1 over 17. 17 over 37, or 0.459 amps. And using Ohm's law, Vx prime is simply Ix prime times 20 ohms. So we multiply this guy by 20, and we get 9.189 volts. Now, what I am going to do right now is solve for it using Ohm's law and the equivalent resistance, because I want you guys to see something. So Vx prime is going to be the current, 1 amp, that flows into the equivalent resistance, which is 1 times, or divided by 1 over 17 plus 1 over 20. They're the exact same expression. Like when we multiply our first expression by the 20 ohms, we have 20 ohms in the numerator and the denominator of that first, of the top thing. And so doing current division and then doing Ohm's law, or just using Ohm's law with the equivalent resistance, is the exact same thing when there's only 2 resistors, okay? Or actually any number when everything is connected in parallel. So current division probably actually isn't the most effective method here, because it actually winds up involving that extra step where if you just did the equivalent resistance, you'd be there in one, okay? So it's not necessarily bad to do current division here. It just involves an extra Ohm's law step, and you can solve this thing using Ohm's law in the first place. All right, so we got an answer. So for part B, we're going to have the current source off and the voltage source on. So how do we turn off our current source? An open circuit, which means not even going to draw it. I'm trying to find that Vx double prime. Here is our 10 ohm resistor. Here is our 7 ohm resistor. And then here is our voltage source, and it is a 5-volt source. So how can we solve for the quantity Vx double prime in this circuit? All right, let me ask you guys a slightly different question that is leading on purpose. We have a node right here and another node down here. What is the electric potential difference, or the voltage drop, between the reddish orange node and the blue node? 5 volts, because there's a 5-volt source. So that means there's a 5-volt difference between this point in the circuit and this point in the circuit. So do we know the voltage drop over that series combination of resistors? Yes, it's 5 volts. So this is a perfect place to apply the principle of voltage division without having to do any extra work. So using voltage division, we can say that Vx double prime is going to be negative. And the reason why it's negative, if you look back at your notes or the video for voltage division, we are expecting, with the positive polarity terminal of the voltage source attached to this node, we are expecting plus minus plus minus, but Vx is defined with the opposite polarity. So we need to include that negative sign. So we're going to have negative 5 volts times 20 ohms over 20 ohms plus 17 ohms. So that's 5 times 20 divided by 37, negative 2.703 volts. Yeah. All right. So now that we know what the voltage Vx is with the voltage source on, current source off, and current source on, voltage source off, to find out what Vx is in our original circuit, we simply add those two answers together. So Vx will simply be Vx prime, which is when we had current source on, voltage source off, plus Vx double prime. So that's 9.187, or 189, excuse me, minus 2.703 is 6.486 volts. For part D, we don't actually have to do any new circuit analysis whatsoever. And that's the beauty of this circuit being a linear circuit, meaning that it obeys both the homogeneity and the additivity principle. So it says if the source were replaced with a 3-volt source, positive polarity on bottom, what is the scaling factor that's being applied to the voltage source? And the reason I'm asking that, and I'm kind of running out of room here, so I'll try to do it up here. So we know that when our input, here's our outputs. So we know that when our input is a 5-volt source by itself, we know that our output was negative 2.703 volts. And when our input was 1 amps with the direction up, we know that our output was 9.189. And when both of them are on, we figured that out as well, okay? Now, my question is, what are we scaling the voltage input by? If we are changing it from 5 volts to 3 volts and changing the polarity. So definitely a negative, and then it's going to be what fraction or whatever? 0.6. Okay, so negative 0.6. So that means we should expect our output to scale by that exact same factor. So negative 2.703 times negative 0.6 means that we should expect to see a voltage of positive 1.6218 volts. And if we scale, so we replace the current source with a 2.5 amp source direction up. So what is our scaling factor for our current source input? 2.5. So we need to scale our output by the same amount. Which is 22.973 volts. And we're trying to find what our voltage Vx is with both of those scaling factors applied with the current source on and the voltage source on as well. So we simply add these two numbers together. .594 volts. We did no circuit analysis whatsoever, but I absolutely guarantee you that if we simulated this circuit or went through it, we would get that exact result. That is the beauty of a circuit being linear. If you can analyze it once and you know how it behaves, you can change the voltages, change the currents and all that kind of stuff, and you're going to know exactly how it will behave as well. All right, so we've spent about 18 minutes on that, and we have a lab to do today. So I remembered to print off the lab sheets if anybody didn't do it. What I would like you guys to do, let's see, there's 3 at that table, 4, so that's 7, 11, 12, 13, plus another 3 is 16, 19, 20, 21, 22, 23, 24, 25, 26. Great. There's 26 people, which means we can easily split up into 2-man teams. So split up into 2-man teams and do the lab. If you need an assignment sheet for the lab, feel free to come up here and grab one. So today's in-class assignment deals with the concept of superposition. Did anybody have any questions regarding this problem, or did you feel it was pretty straightforward? You'd like to see it. All right. So using superposition means that we're actually going to work this problem twice because there are 2 independent circuits, or excuse me, 2 independent sources in it, okay? So we're going to work it once with the current source on and the voltage source off, and then again with the current source off and the voltage source on. So let's do current source on first. Oops. So we have 17 ohm resistor in parallel with a 1 amp source. We have a 20 ohm resistor, positive Vx, and I'm going to call it Vx prime. That lets me know that it's not the total Vx. That's just my notation that I choose to use. Here's my 10 ohm resistor. Here is my 7 ohm resistor. And lastly, how do I turn off a voltage source? Did anybody watch the lecture and figure that out? Short circuit, thank you very much. So we turn off our voltage source by replacing it with a short circuit. So this is what our circuit looks like with the voltage source off and the current source on. So I'm open to any suggestion that you may throw out about how we could solve for that voltage Vx prime. So let me ask you guys a slightly different question. The 10 ohm resistor and the 7 ohm resistor are connected in parallel with that short circuit. So what does that do to the 10 ohm resistor and the 7 ohm resistor? What happens when you have stuff in parallel with a short circuit? So let's try to combine them. What's the resistance of a short circuit? 0 ohms. So the equivalent resistance, looking at the 10, the 7, and the 0 ohm resistor effectively right here, is going to be 1/10 plus 1/7 plus 1 over 0 to the -1 power. So we have a 10th plus a 7th plus infinity, which is going to look like infinity, to the -1, which is 0 ohms. So whenever you have a short circuit in parallel with resistors, you can treat those resistors as if they were open circuits. Effectively throw them away. They're not contributing anything. So this guy doesn't do anything, and this guy doesn't do anything. So any current that's flowing through the 20 ohm resistor is going to go around those guys like so, okay? So all the current's going to flow through the short circuit. None of the current will flow through the 10 ohm resistor or the 7 ohm resistor. That's how short circuits work, and that's why they're so dangerous in electrical circuits, like in real electrical circuits and stuff like that, because if you have a short circuit, you might be sending a large amount of current through something that's not designed to be able to handle that large amount of current. It can cause fires, shocks, all that kind of good stuff. All right, so now what we're left with is effectively a 1 amp source in parallel with the 17 ohm resistor in parallel with the 20 ohm resistor, and we're looking for the voltage drop over literally anything because they're all in parallel, so they share the same voltage. So how might we go about solving for that voltage? So KCL, Kirchhoff's current law, would be us adding up currents. So how would that help us find a voltage? All right, so the 5-volt source is turned off, which is why it's a short circuit. So if we did KCL, let's do it, I guess, at the top node and say that we're trying to find this current and we're trying to find this current. So that would be 1 amps flowing in is equal to, so what's the current directed to the left in terms of Vx prime? So Vx prime will be, sorry, single prime, will look like that, right? Positive polarity terminals connected to this node, negative polarity terminals connected to this node. So if the current's flowing into the positive polarity terminal, positive, all right? Positive what? Both the currents going to the left and to the right are going to be positive because they both flow into the positive polarity terminals. Yeah. So how are we going to express, we know that they're positive. What is the current in terms of Vx prime? So Ohm's law is V is equal to I times R. We want I, so that means it's V over R. So I ask again, what is the current flowing through the 17 ohm resistor in terms of the voltage Vx prime? Excuse me? All right, Vx prime over 17 ohms. What about the current flowing through the 20 ohm resistor? Vx prime over 20 ohms, alrighty. And so we could do some algebra here, and this would be 1 amp, let's see, divided by 1/17 plus 1 over 20. Is that right? So hold on, so this would be Vx prime multiplied by 1/17 over 1/20. Yeah, so then I divide, and that is equal to Vx prime. So what may not be obvious to you guys looking at this, this is actually, what's if I wrote this as 1 amp times 1 over 17 plus 1 over 20, what am I doing? No, current division would have something in the numerator that isn't just 1, unless we were dealing with a 1 ohm resistor. That's the equivalent resistance of those two guys. Okay, so even if you do KCL, you wind up getting the exact same expression as you would have gotten just using Ohm's law. If you do current division and then multiply by the 20 ohms, you get the exact same expression you would have gotten using Ohm's law. Whenever you have a current source in parallel with resistances, it's probably easiest just to use Ohm's law, where the current multiplied by the equivalent resistance gives you the voltage drop over everything. So you can absolutely rely on simple stuff like that. All right, so to that end, let's numerically solve here, right? So somebody tell me, throw it in their calculator and tell me what's what. All righty, 9.189 volts. All righty, so now we're going to rework the problem with the current source off and the voltage source on. And I'm kind of running out of room, so I'm actually just going to put it here. 9.189 volts is equal to Vx prime, and then erase some of this stuff. All right, so current source off, voltage source on. So how do I turn off a current source? An open circuit, thank you, ma'am. So an open circuit between here and here is effectively just nothing, right? Just air between those two places. So I don't even really need to draw these terminals. Positive Vx double prime, 10 ohm resistor, 7 ohm resistor, here, a 5 volt source. So what would be the most efficient way to solve for that voltage Vx double prime? Anybody have any suggestions? Pardon? So if I combine the 7 ohm, which resistors are you talking about? Let's start there. Right, which is the voltage drop over the 20 ohm resistor. So if I combine those two parallel resistances, how does that help me? So let me explain what I mean by that. All right. So we have this top node. And we have this bottom node. And we know that the potential difference between the top node in red and the bottom node in blue is exactly 5 volts. If we combine those resistors, we still know that the potential difference between the top node in red and the bottom node in blue is 5 volts. That doesn't give us any useful information. Now, knowing that there is a 5 volt potential difference between the top node and the bottom node means that the difference between this point in the circuit and this point in the circuit is known. So we have a known voltage drop over the series combination of the 20 ohm resistor and the 17 ohm resistor. That is just begging for us to use voltage division, okay? Whenever we know the voltage drop over resistors in series, and we're trying to find the voltage drop over one of those resistors, voltage division is by far the easiest method to figure that out. So using voltage division, we can say that Vx double prime is going to be negative, and I want to explain why that is, even though we talked about it, or I talked about it in the video lecture. Voltage division is defined to where we have, let's say we have 2 resistors in series, like so. Okay. Call this guy R1, call this guy R2. This is the polarity of our known voltage. Let's call it Vs. And so we expect to see that the voltage drop over resistor R1, positive polarity terminal is connected to positive polarity terminal, and then the voltage drop over resistor R2 is like so. So we're effectively saying that the sum of the resistor voltages has to be exactly equal to the source voltage, right? The polarity that we have assigned to Vx double prime, which is part of the problem statement, is opposite that of what we would expect when using voltage division, right? So we have the source voltage, the positive polarity terminal of the source voltage is connected to the negative polarity terminal of a resistor voltage. So that's why we have to include this extra negative sign here, okay? Because the polarity of the resistor is opposite that of what we would expect using voltage division. All right, so, and I believe I explained all that and did some examples with it in the voltage division video thing. All right, so we have negative, our source voltage, 5 volts, times the ratio, where the ratio is the resistor we want is in the numerator, so that's 20 ohms, and then the total series resistance seen between our 2 points where we know the voltage is in the denominator, so that's 20 plus 17. So this is going to be negative 100 over 37, which is negative 2.703. So now that I know what Vx is with the current source on and the voltage source off, and I know what Vx is with the current source off and the voltage source on, how do I determine the voltage Vx with both sources on without doing any more circuit analysis? You add them together. It's that simple. So Vx is simply Vx prime plus Vx double prime, which in this case turns out to be 6.486 volts. Now part D is really just kind of a word problem, and we're not going to use any more circuit analysis for it either. What I'm going to do instead is try to sneak in a small table here. Inputs on one side, outputs on the other. So we know that when the 1 amp source is on, our output was 9.189 volts. And we know that when the 5-volt source was on by itself, our output was negative 2.703 volts. So in part D of this problem, we are told that if the voltage source were replaced with a 3-volt source, positive polarity on bottom, okay? So what we're doing is we are scaling our original 5-volt source to be a 3-volt source. So what number do I need to multiply 5 by to get 3? Let's start there. 0.6. And I'm changing the polarity of my voltage source. So what do I need to do that? A negative sign, right, okay. So we're multiplying our 5-volt source by a scaling factor of negative 0.6. And because this is a linear circuit, we can then scale our output by that exact same factor without having to do any extra circuit analysis. It has to work that way for a linear circuit. And a linear circuit is really any circuit that the components values don't change with time. So if we multiply this guy by negative 0.6, what we'll find is that the expected output with the 3-volt source on with the opposite polarity is, let's see, let me erase all this crap, negative 2.703 multiplied by negative 0.6 gives us positive 1.622 volts. Now, the next part of the problem statement says the current source is being replaced by a 2.5 amp source direction up. So what's the scaling factor that we're applying to our current source? Positive 2.5, right? The direction's the same, so we don't need to change the sign. So if we multiply our input by 2.5, we can also multiply our output by a factor of 2.5. 9.189 times 2.5 is 22.973 volts. And if we add these two guys together, we get 24.594 volts. So that is what the voltage Vx would be with this circuit, but we replaced the 5-volt source with a 3-volt source, opposite polarity of what we originally had, and we replaced the 1 amp source with a 2.5 amp source, okay? We didn't do any extra circuit analysis whatsoever. We could simulate this circuit or go through all the work and figure out that we would get the exact same answer, but I'm not going to spend the time doing that right now because A, we have a lab, and B, I know that this is correct, okay? That is the beauty of superposition and linearity. You could technically work every problem in this class by replacing all of the voltage sources with 1-volt sources and all of the current sources with 1 amp sources, and then scale things appropriately and get the correct answer 100% of the time, okay? So superposition and linearity is a very, very powerful tool. Unfortunately, we're not really going to use it a whole heck of a lot in this class until later on. We're going to be learning nodal and mesh analysis next. Students typically gravitate towards mesh analysis pretty strongly. But when we get to the last section of the class where we're dealing with complex numbers, and since your calculator can't solve systems of equations with those, we're going to have to go back and rely on tools like superposition and stuff like that to be able to actually work the problems. All right, so that's the in-class assignment. Hopefully it was fairly straightforward, or at least once I showed you how to do it. It seems like an awful lot of people didn't watch the video. I can tell you right now that you're going to fall ludicrously behind if you continue that practice. So take the time, watch the videos, all that kind of jazz, or expect to bomb the bejesus out of the test. It's just that simple. All right, so we have a lab today, and the lab is regarding resistor combinations. So I sent you guys an email letting you know to bring your kit and all that kind of jazz. If you did not bring a multimeter, there are multimeters in that cabinet over there. I'll open it up momentarily, and all that kind of stuff. If you didn't happen to print out a copy of the lab assignment sheet, I have a stack of them up here, so feel free to just come by and grab one. So let's see, 2, 4, 6, 7, 8, 9, 10, 11, 15, 18, 22. All right, so there are an even number of students, so everybody should be paired off just 2-man groups and take care of this. If you have any questions, I'd be happy to answer them.